Last week, SpaceX engineers discovered a critical flaw. It threatened to disable thousands of Starlink satellites. But what happened next reveals an engineering solution so brilliant, it is changing the entire aerospace industry. I have analyzed the technical data. Today, I am breaking down exactly how SpaceX's team turned a potential disaster into their biggest breakthrough yet. Here's what most people missed. When SpaceX launched their latest batch of Starlink 5-2 satellites, they discovered a massive problem. The inter-satellite laser links were degrading 40 times faster than expected. At this rate, nearly 30,000 planned satellites would become deadweight in orbit. The cause was a quantum effect that no one saw coming. The problem was not the lasers themselves. It was how they handled thermal expansion in the vacuum of space. Every time a satellite moved from sunlight to Earth's shadow, the temperature swing created microscopic misalignments. Multiply this across thousands of satellites, and you have a $10 billion constellation slowly going blind. But here is where SpaceX's engineering team proved why they are the best in the business. Instead of trying to fight the thermal expansion, they turned it into an advantage. They developed what I call the quantum lock system. Here's how it works. Traditional satellite communication systems try to maintain perfect alignment at all times. That is like trying to shoot a laser pointer at a target while riding a roller coaster. It is nearly impossible. SpaceX's solution? Let the system move, but make it move in a predictable way. They redesigned the laser housing to create controlled thermal deformation. When the satellite enters Earth's shadow, the housing does not just expand or contract randomly. It follows a precise pattern. Think of it like a mechanical watch that uses temperature changes to keep better time. The results shocked even SpaceX's own engineers. Not only did this fix the degradation problem, it actually improved the system's efficiency by 23%. The laser links now automatically adjust themselves using the same force that was trying to destroy them. But here's the genius part that nobody is talking about. This solution requires zero extra power. In space, every watt of power comes at a premium. SpaceX found a way to let physics do the work for free. It is like turning your car's waste heat into extra horsepower. Let me break down exactly how this system works at the molecular level. When spacecraft materials heat up in sunlight, their atomic structure actually expands. Most engineers see this as a problem. SpaceX saw an opportunity. They used what materials scientists call programmed deformation. The numbers here are staggering. Each Starlink satellite experiences temperature swings of over 200 degrees Celsius in a single orbit. Traditional systems would need complex mechanical compensators just to maintain basic functionality. But here's where it gets interesting. These temperature changes happen in a perfectly predictable cycle. Every 90 minutes, the satellite orbits Earth. SpaceX's engineers tried 3 other solutions before this breakthrough. First, they attempted active cooling, but that consumed too much power. It ate up about 40% of the satellite's entire energy budget. Then they tested advanced composite materials that were supposed to resist thermal expansion. But these proved way too expensive for mass production, and they increased cost without solving the problem. Their third attempt used mechanical compensators. This is similar to what NASA uses on the James Webb Telescope. But with thousands of satellites, the failure rate was just too high, and reliability would not scale. Before rolling out the quantum lock system across their entire constellation, SpaceX needed to be certain. They conducted extensive testing in their thermal vacuum chamber, and they pushed the system far beyond what it would face in actual orbit. The test satellites were subjected to temperature extremes that would cripple traditional systems, from a bone-chilling minus 150 degrees Celsius to a scorching plus 120 degrees Celsius. What they discovered was remarkable. Not only did the system survive these extreme conditions, it actually performed better under stress. This counterintuitive result reveals another genius aspect of the design. The more extreme the temperature swing, the more precise the alignment became. Why? Because stronger thermal gradients create clearer, more predictable deformation patterns. It is like how a sundial works better on a bright day. The stronger the signal, the more accurate the system. This breakthrough isn't just changing how satellites operate. It is revolutionizing how they are built. Traditional satellite manufacturing requires incredibly precise assembly in clean rooms. Components must be aligned to tolerances smaller than a human hair. This painstaking process is one reason why satellites are so expensive. But the quantum lock system turns this entire approach on its head. Because it is designed to work with thermal deformation rather than against it, tolerances can be looser, satellites can be built faster, the system handles the fine adjustments automatically once in orbit. This could reduce manufacturing costs by up to 60%. At the same time, it improves reliability. Instead of trying to eliminate material imperfections, they are embracing them. It is like how a tree grows stronger by adapting to wind stress. The very thing that should make it fail actually makes it more robust. The applications of this technology extend far beyond Starlink. Imagine space telescopes that automatically adjust their optics based on thermal conditions. They could achieve unprecedented clarity without complex mechanical systems. Or space stations that use thermal expansion to maintain perfect solar panel alignment. This maximizes power generation without any moving parts. The Department of Defense has already expressed interest. They are looking at adapting this technology for their next-generation surveillance satellites. The system's ability to maintain precise alignment without active control is ideal. Sensitive optical systems cannot afford any mechanical vibration. But perhaps the most exciting potential lies in deep space exploration. As we push further into the solar system, spacecraft face increasingly extreme temperature variations. Traditional systems struggle with these conditions. But this new system actually becomes more effective in more extreme environments. For a mission to Mars, or even the moons of Jupiter, this is a game changer. This kind of passive, self-correcting engineering is the holy grail. It means fewer moving parts to break, less power to generate, and a much higher chance of mission success. We are watching history being made here. This isn't just a fix, it is an entirely new approach to space engineering. It will influence satellite design for decades to come. Next week, I will break down exactly how SpaceX is implementing this system across their entire constellation. I will also cover the surprising role that machine learning plays in the process. Hit subscribe and turn on notifications right now. This is the kind of engineering innovation you don't want to miss. This is Infinite Approach, where we solve the biggest problems in space. See you in the next one.